Gone. All right, now next we have Faray and Alex. Let me bring them up. Okay, Faray, invite. Okay. All right, Faray, please accept. And then Alex, please accept.
Okay. So present, select a PDF file, /.
And your camera is not on, Faray, if you want.
My camera is not on.
No.
Okay, my camera. Can you see me? And can I move my mouse, or there's no mouse or pointer or whatever, or is there a pointer?
I'm not seeing a mouse. Can you move it over your?
No,
I'm not seeing it.
Okay, well, I have to do without a mouse then. I'll start. Hi, I'm François-René Rideau. I'm presenting today a work I did with Alex Knout and Nada Amin about prototypes, object orientation functionally, in which it's a paper in which I argue that these two definitions here are the heart of object orientation. And to make them easier to explain later, I will just rename.
Just lost your audio there.
To make I can rename a few of these labels, and we'll explain that later. But basically, we're arguing that this is the heart of object orientation. The paper has a series of definitions of object systems of increasing sophistication. And these definitions can be usable, but they're also mostly used to illustrate fundamental concepts in object orientation. So what are the concepts? What does inheritance mean? What are prototypes and what are classes? And we'll argue in this paper that prototypes are more fundamental than classes. And so we do everything with prototype first and then with classes. We also argue in this paper that object orientation at heart is best expressed in pure functional programming, and that this comes first. And we can also adapt things to mutation and the context with our side effects. But the heart of object orientation is better understood in the context of pure functional programming. And we provide a constructive semantic. That is, we have definitions. The definitions give you mathematical equations that help you reason about your programs and about what object orientation is. And the same definitions are a runnable implementation that is reasonably efficient or can be made so with little changes. What is not in the paper is my hot takes. So my first hot take is, what is object orientation about? And I think it's about two things. The two lines, and each of these lines can be viewed in two ways, left and right, the two columns. And the first thing it is about is incrementality. When I write an object-oriented program, what I want to be able to do is write small snippets of code. That's incrementality. And each snippet only deals with one aspect of the code. And for all the other aspects of the code, I want to refer to something else, to a previous object. I want to inherit from it, or I want to inherit from an object that is maybe not yet defined, but I will want to defer the other aspects to something else, to other parts of the specification. And when I look at incrementality, that's looking at incrementality from the point of view of the user of the white program, and from the point of view of the implementer, the person who implements object orientation. This will correspond to open recursion. That is, I will have operators that will take a self, a variable, as a variable, and it will do something with that self and return something. At the end, we'll change those operators and we'll take a fixed point to have the self. So all those increments will talk about the same self. And that's how we do open recursion. That's how we implement incrementality. And object orientation is also about modularity. Modularity is the fact that all these increments, you want to write them in such a way that when you make a change here or a change there, it doesn't trickle to plenty of changes everywhere. And in terms of practical implementation, that's what people call ad hoc polymorphism. That is, you want to have some notion of interface, and the same interface can be implemented by different implementations. Okay, so What is object orientation not about? Object orientation is not about classes, and that's easy to prove. There are plenty of object-oriented systems that don't have classes. Therefore, you don't need classes to have object orientation. That does not mean that classes are not important. Classes are a very important concept in object orientation, just not what it's about. Just like types are not essential for functional programming. You can have functional programming without types. Types are still very important. You want to have types sometimes, but you can do functional programming without types. There's even a programming language called Scheme that doesn't have any static types, and plenty of people use untyped lambda calculus. And we'll see that there's actually a formal relationship between classes and types, and we'll get back to that later. Some things that object orientation is not about is encapsulation. Plenty of people talk about encapsulation, which is a way that to control which part of a program can access which other part of a program. You can have object orientation without any specific encapsulation in Smalltalk or in Common Lisp. You can also have encapsulation without any object orientation with namespaces, scoping, functional abstraction, all these things in functional programming languages. Therefore, encapsulation is a totally orthogonal topic to object orientation, and those who pretend otherwise are just scamming you. Also, object orientation is not about some kind of rivalry between inheritance and composition, where, oh, we have to do everything with inheritance or everything with composition, and if you can't replace one with the other, then it's worth nothing. These are different concepts. Therefore, sometimes one applies, sometimes the other applies, and it's absurd to try to replace one concept with a different concept. They are not substitutable. The whole point of having different concepts is to use them in different situations. Finally, it's not about mutation. A lot of people are introduced with object orientation in the context of mutable objects, where side effects, where even to initialize an object, you need to initialize to side effect the fields. In many languages, that's the case, but this is not at all what object orientation is about. You can have object orientation without any mutation whatsoever. I have many examples, and we'll get to it. And therefore, just because historically everything was imperative because machine resources were very scarce and you couldn't afford to do functional programming, well, since the 90s, it's not the case anymore, and you can have, and it's actually better to understand object orientation without mutation. Okay, so what are the fundamental concepts that I introduced in this paper and that I try to explain in the paper? The incrementality, and we'll spend some time in this talk about discussing about what I call instances and prototypes. Maybe I'll change the names later in the future paper, but that's the name I have now. Well, in the paper, I discuss also inheritance, both single inheritance and multiple inheritance, and actually also mixed inheritance, the first one I will see. I will, in this talk, gloss over a lot of it because I don't have time. We'll also discuss in the paper the generality, that this notion of instances and prototypes applies to many things beyond records, where a record is a mapping from, say, labels to values. Well, we can do much better than that. Object orientation, or at least the prototypes, and is much more general than that. I want to also discuss a key concept that most people miss when they discuss object orientation is what I call the conflation between prototype and instance. And at the end, we'll discuss types and classes and things like that. So what is the simplest way that we can do incremental programming? Like, if you want to reduce that to the core concept in functional programming, how do we do that? Well, we want to have two notions at least. A notion of instance or value, which is the thing that you want to specify incrementally. You want a incremental specification, you want to specify something. And then you will have the notion of this incremental specification that right now we're going to call a prototype. Okay, so you have these values, these instances, and those prototypes, those increments. So roughly, you will want two operations. You will want an operation instantiate, which informally will take a prototype and maybe some extra context and return the instance, the value. And then you will want an inherit operation that kind of composes prototypes together. So maybe one, maybe two, maybe n prototypes together. But the simplest case would be two prototypes. So I want to take two prototypes and get one prototype. Some people call these things mixing instead of prototypes. That's in the literature, there are many variations. So what is the simplest instance we can choose? We want a record. A record typically is a mapping from a symbol to a value. In other languages, it could be a mapping from integers to values, or from string to values, or if you're more advanced, from hygienic identifier to value. But in any case, you want something that has a decidable equality. And the simplest example would be something like my point. That's an obvious example, where you want a point with two coordinates, say x and y, to fields, and you implement that as a function that takes a message. This message will be the name of the field you want, or the identifier for the field you want the value of. And if the value is x, I will return 1. If the value is y, I return 2. And otherwise, I will throw an error. So then I can ask my point, what is your y coordinate? It says 2. And now, what is the simplest kind of prototype, the simplest kind of mixing? In the literature, I think William Cook, in his 89 thesis, called that a wrapper. And if you look at the type of it, this kind of prototype is a function. The type of a prototype is a function with two parameters, super and self, where there's such that we have this constraint that self is a subtype of super. And then this prototype will basically take a self argument and a super argument and return the self argument. The point being that you will want to compute the self as some kind of fixed point, and super will have all the things that you inherit from the previous prototype, from the previous incremental definitions. So how do you instantiate then a prototype? You take a prototype and a base object. So the base object would be of the type super of your overall definition. That's the base object, the supermost. If you have a chain of prototypes, it will be the base object, the super, when there's nothing left. Typically, it will be an empty record. And then you want to take the fixed point. So why can't I just define self proto of self base? That's what I would want to do. Unhappily, or happily, Scheme is an eager language, an applicative language, which means that if I try to define self proto self base, the value self passed to proto is an initialized value of self before you do the define. So this is not going to go well. In an applicative language like Scheme, I need to protect the reference to self inside this lambda. So lambda I apply self I is just an eta conversion for self. It has exactly the same behavior as a function as self, except that it protects the access to the self variable. I could also use a delayed value here in Scheme, and actually we'll use that later. And so it just takes self as a fixed point of proto applied to self and base. Easy. And the second thing we want is a method to compose, to mix those mixing, to compose those prototypes. And we call that inherit here. And this function inherit takes two parameters, which are a child and a parent. Child and parent are two prototypes. The first is a prototype from self to super, say, and parent is a prototype from super to super 2. And what you return is a new prototype. A new prototype is a function from self and super. And know that self and super are instances, they are values. They are the type of the thing you're going to define. Whereas child and parent are prototypes. They are functions from self and super to self. So different types. So child and parent are prototypes, self and super are values or instances. And the way you change them is the obvious way. You want the same self argument. So the self argument of child is the same as the self argument of parent. On the other hand, you want to change the super. You want to change the thing that you inherit from. So parent gets the super that is passed to the overall combination, whereas child is passed as a result of parent applied to self and super. So this is, if you look at the type, if you look at what it should be, if you look at the literature, this is all simple and obvious. When you get shorter identifiers, it's just 100 characters of Scheme. It's very simple, and it has all you need to know about object orientation. How do you use it? So let's take back the same my point definition. So we pass an object, can be x or y. X is 1, y is 2. Let's define a few prototypes, a few mixins. And I will put $, as my convention for the name. The first mixin is just, I'm going to override or create a new variable x, a new field x, bound to 3. So I look at the message. If the message is x, I return 3. Otherwise, I do the default thing, which is pass the message to super. Here is another prototype that is double X. What does double X do? It takes the message. If the message is X, it asks the super, what is your X? And then it multiplies that by 2. So we can inherit a value from the super and modify it. And otherwise, we use super, the default, super message, the default thing. We pass along the message, we pass along the buck. The last kind of prototype I want to show is one that uses the self in a non-trivial way. So let's say we have a point that has x and y coordinates that are reals. I want to return a complex number z that is just x plus I times y. And in this case, I take the message. And if the message is z, then I will pass along x to self. So then I will look at the x coordinate. I will pass y to self to get the y coordinate, and I can do the linear combination of them. Otherwise, I continue. And as you see, x and y can, not only can, but must be defined by some other aspect, some other prototype, or by the based object. Otherwise, it will be undefined. But we go back to the top of the object to know what is the x of the top of the object. We don't ask x from the super object. We ask x from the other thing. That allows us to have prototypes that can access some aspect of your object and define another aspect of the object. Let's combine all these things together. We can make a your point prototype for point that mixes, inherits via inheritance these all three prototypes, which when evaluated, by the way, go right to left because it is a scheme. So the way you compose things is right to left. And let's define your point by instantiating this prototype with the base object my point above. And so x starts as, we start at x1, y2. We then set x to 3, so it becomes x3, y2. We double that, so it becomes x6, y2. And then we compute z as x plus I times y. And indeed, it's 6 plus 2y. There we go. And you can redo all of object orientation, all the usual things that way. The paper has much more elaborate examples. But this is to show you that, yes, these very simple definitions work. Single inheritance, I'll gloss over this slide because I don't have time, but basically it's what we have before is what some people call mixing inheritance. Single inheritance, and in mixing inheritance, you can compose those mixins. In single inheritance, you can just apply those mixins to a base. And so it's much poorer. Instead, it's just having only cons instead of having append. So with mixing inheritance, you can append your list of prototypes into a new list of prototype. With single inheritance, you can only count, you don't have append. Okay, beyond simple records. So you may notice that prototypes do not have to define records as a function from symbol to value. It can be any kind of function. It could be, even with a bit of adaptation, any kind of value if it's delayed or lazy. And if you're familiar with Paul Blanc-Levy's paper, Call by Push Value from 1999, where he has a unifying paradigm for both call by value and call by name, you recognize that prototypes are about building computations. They are not specifically about building values. That's why when you want to name what it builds as an instance of value as a value, you need to make it into a function, a thunk, a delayed value, a lazy value, because at heart, prototype and object-oriented programming is about incrementally specifying computations. If you want a record and the usual OO, you need to have subtyping or dynamic types, but you can also use prototypes and this object orientation without any kind of subtyping. It's just, of course, more limited in other ways. Multiple inheritance, I don't have time to go about it, but I will just say that your wrappers or your mixins sometimes depend on other mixins, and you want to make this dependency modular. That is, you don't want to, when you have mixins all over the place, define many modules, you don't want to have to remember which mixins the person that you uses in terms, and you want to have a simple dependency graph and have this dependency graph linearized into something automatically for you. You don't want to track who is using your modules and which other modules you're using. And so multiple inheritance makes modular these dependencies in a way that is not modular otherwise. Read the paper for more. Here's the key point of this presentation, probably. The point that most people miss when they understand or they try to understand object orientation. Certainly, I missed this point for 20 years at least, and I was totally confused by what object orientation is or isn't. And when I finally understood this point, it was, wow, now I understand object orientation. So in what I've shown you, we had instances, which are arbitrary computations, and we had prototypes or mix-ins, and we didn't have object. We could do arbitrary, all the kinds of things you can do, the incremental programming you want to do with object orientation. I could do all of that and not have anything called an object. I had prototypes, I had instances, and that was all. And sometimes that's enough, but sometimes that means that if you have a nested data structure with lots of things that know that, am I an instance right now or am I a prototype right now? And you have to track down which is which every time. It can be very cumbersome to do that and takes exponentially much effort, either by the machine or by the programmer to clarify what is an instance or what is a prototype at which point. And the solution is obvious. You want to manipulate both the prototype and the instance at the same time, and you call that an object. And you may have noticed that in a pure functional language, the instance can be deduced from the prototype. You just take the fixed point. There is only up to equality, observational equality, there will be only one instance, modulo side effects. If we imagine that there are no side effects, you have one instance per prototype. So it's just basically caching the fixed point for your prototype, assuming that the base object is given also. So maybe it's prototype times base as instance. But so you want to manipulate these things together, the prototype and the instance, and you call that an object. At least in prototype object programming, that's what we call an object. And of course, if you don't understand that there are two separate concepts of prototype and instance, and you're given this object and you are told what is the semantics of objects, and you don't even have an operator to decompose this is a prototype of the object and this is an instance of the object, you'll be totally and utterly confused. And that's what I was. Before you can understand this conflation of prototype and instance together, you have to understand the separation, the two concepts separately first. And that's the key to understanding OOP, according to me. And then classes become trivial. What is a class? A class is prototype object orientation at the meta level. It means that the most, or one of the most useful things that you may want to write incrementally is type, an abstract data type with its operation. It has a field, it has operation, maybe it has multiple types associated that come together, and that's what you want to describe incrementally, an algorithm that has types associated to it. And that's what you can do with prototypes. At the meta level, you invent whatever method you want to describe your types, and you define that incrementally with the usual prototype object-oriented methods. And there you have a class is a prototype for a type descriptor. And the concept is so useful that even people who confuse prototype and instance without conflation and without distinction, they reinvent the distinction. They say, oh, if I'm only going to be interested in this class as a prototype, I will call that an abstract class. And if I'm only going to be interested in this class as an instance, as a type, I will call that a concrete class. But if they had not done this confusion to begin with, they would not have to then try to unconfuse with weird names and things like that. Another thing you gain by understanding that class OO is just prototype OO at the meta level is that you don't want to have this absurd, obviously false equation between subclassing and subtyping. Subclassing means that your prototype is in some sense a subset of the other prototype, or your chain of prototype is a subset of the other. And subtyping means that the type being described is the subtype of the other, type being described by the usual subtyping relationship where the elements of one are the elements of the other. And obviously, there's no reason why these two orders should commute with a fixed point. A fixed point does not preserve these order relationships. So trying to put that either as an equation you want to prove or as a constraint on your language, however you put it, is totally absurd. And people who pursue this goal are pursuing just like totally wrong goal. Additionally, I will say that since all this in class objects, in class OO happens at the meta level, it's all pure. You don't have side effects of classes at the meta level, at least no user visible modifications of the classes. Maybe multi-methods monotonically increase what you know about the class it adds methods, but in all these compile time OO of compile time prototype for type descriptors, you don't have any mutation. Therefore, the pure functional semantics for OO totally applies. There's a caveat at the end, is that the way the word objects and instances are used traditionally in Java and other object class-based oriented languages is very different from the way I have been using object and instance so far in my talk, whereas it's more in the line of prototype object language. What I've called an object, what I've called an instance is just a value of which you compute the fixed point that you value. So it's an arbitrary computation. And what I call the object is this conflation of prototype and instance and anything else together. Whereas what they call object or instance in Java and others is an element of the type being described as a value of your class as the instance. So that's confusing. Maybe I should in my future papers rename those things to avoid the clash of names. But you should be
sorry.
Yes.
Sorry, just a time check. 3 minutes.
Oh, 3 minutes. Okay. Mutation, I'll go over it. With some things become easier or harder with mutation, you can support both. Constructive semantics, with my method, you can have in 30 lines of code your OO language in any lambda capable language. With 50 more lines of code, you have multiple inheritance. We don't need any side effects except laziness, which is not a side effect. Related work, plenty of them, read the paper. Oh, future work, read the paper, plenty of things to do. And to restate the paper, we defined a series of object systems and we understand OO thanks to that. But I have a meta claim that lots of people in the past have been, oh, we are FP, we're anti-OO, or we are OO, we're anti-FP. And then we talk past each other. We don't even understand what the other is talking about. There's a lot of fanaticism online, and there should be much more humility, including in academic circles. If you can't even understand the value of the other, and obviously the other has some value to someone, maybe your paradigm is too narrow. You should go wider. If you are into OOP, you should start, yes, maybe logical consistency has some value. Maybe closure, higher order functions has some value. If you're into FP, maybe my simple Hindley-Milner type system from the 80s is not sufficient and I should go wider, have dependent types, subtyping, whatever. So just listen to each other and don't be so fanatic. And Scheme is great here because it allows us, with having lambdas from semantics and macros of the syntax, to really go to the heart of the semantics and make the thing practical. And then you can go really to the heart of the thing where things are very simple, the concepts are small, and you can really understand what's going on. So if you have questions, I have this paper, I have a practical implementation that I'm using in production in Scheme, which is a mutable variant of it. I have a pure variant in Nix, and we're hiring at Mutual Knowledge Systems. Thank you. And sorry, not that much time for a question.
Thank you, Farai.
Thank you. I think we do have a couple minutes for questions. So.
Yay!
And if you have questions, you better ask them fast. Otherwise,
yeah.
I'm going to.
That's right. And a reminder, if you have a question, please type it in the Q&A tab.
How does this compare to the OO system in T? Actually, T is one of the first things that implemented exactly the system. T does not have composition of mixins, so it's but this is basically the same system as in T. Yes, basically the same system as in T, but yeah, read the paper. Yes.
Thank you.
But our version is pure and has composition in T's lower level mutation. One guy who did a lot of these things well is Gilad Bracha from the Smalltalk Newspeak, whatever community. So you should also read his stuff. He's a lot of the ideas in my paper are either explicit or implicit in his work.
Okay, question from Owen.
I'm sorry. Yes, I'm sorry. I did not read Oaklist, but I read some. I tried to read some documentation. It was not clear enough, and I didn't dig into it.
You can do even better than reading the paper. You can
Talk to Park. Yes.
No, even better. It's out in Git somewhere. It's open source.
Yes.
And it comes with a VM written in C. You could run it today, even though it was written 30 or 40 years ago.
So how does it compare to T? If it's the same thing as T, the same thing as T.
It's way more complex, and we can talk about it. Since we're over time, I'm going to shut down.
Okay.
So I'll stop there, but we can kick this around later, especially since we both live in Boston. All right. Well,
thanks.
Thank you, everyone. Are we? Is it break time? I think it's break time. Yes.
It is break time. We've got half an hour or 29 minutes, and then our final session will begin. So we'll have John Cowan talking for half an hour about the R7RS process scheme standardization and all that. And then we'll end with an hour-long talk by Jerry Sussman talking about layers and sort of more higher-level philosophical talk about the nature of programming and engineering and all those sorts of good things.
To my great regret, I need to be dropping out of the workshop now, so I'll be, in order for some travel arrangements, so I'll be handing off to Will. He'll be running the workshop solo after the break. Thank you, everyone. It's been lovely.
Thank you, Olin. Thanks for co-organizing the workshop. And
Yes.
just as a reminder, when we take a break, you can go to the lobby, and there's a Scheme Workshop table, Scheme Workshop Table 1, or if there are too many people, you have to go to Scheme Workshop Table 2, and you can hang out and have a conversation. And so I encourage you to do that, and I encourage the speakers to go to the Scheme Workshop table as well. And you'll get a notification when we restart the session for the last two invited talks. Thank you very much, Farai.
Thank you for having me. Thanks for organizing, William and Olin. And thanks, Alex, for your help with everything. And Nada, my other co-author who's traveling, couldn't be here today.
All right, let's take a break.